Hi there. In this lesson, we will learn about some early ideas in semantic segmentation through the use of superpixels. The term superpixel is used to describe a group of pixels similar in color or in other low-level features. The pixels in an image are artifacts of discretization, digitization of the natural image into a binary representation for the computer, and they are not any inherent natural aspect of the image itself. Neighboring pixels are likely to have close semantic relationships and share similar information. So grouping pixels into superpixels can therefore be a way to reduce complexity in our network. Low-level computer vision problems, such as semantic image segmentation, involve assigning a label to each pixel in an image. This can be considered a dense classification task. We are classifying what class of object each pixel in the image belongs to. While the feature representation used to classify individual pixels plays an important role in this task, it is similarly important to consider factors at more global levels in the image. Factors such as image edges, appearance, and spatial consistency. We consider these factors while assigning labels in order to obtain more accurate results. The context surrounding a pixel is very important when assigning it to a class. We can see, therefore, that designing strong feature extractors is a key challenge in pixel-level labeling problems. There are various approaches to this. The use of bottom-up grouping of image cues, top-down approaches using object detectors, and CRF approaches, where we encode segment relationships using conditional random fields. These bottom-up approaches are concerned with grouping nearby pixels according to some local homogeneity, or visual cues in the image. They commonly rely on techniques we saw earlier in the course, such as k-means and watershed, edge and contour detection, region growing. And superpixels are a particularly interesting category, as they are perceptually more meaningful than pixels. Furthermore, they reduce complexity in the data by capturing important relationships between pixels and shrinking the data in dimensionality. Predicting the class of each pixel independently from its neighbours often yields noisy predictions. A simple improvement upon this is to force local regions of spatially related pixels to be assigned a single label. There are a variety of methods and techniques for extracting superpixel patches from an image. These techniques should obviously have the goals of being quick and computationally cheap to generate. But more importantly, they must respect object boundaries and not impinge upon the achievable performance of subsequent processing steps. Top-down approaches include using object proposals and image pyramids, our multi-scale sliding windows from earlier in the course, to extract features and perform object detections. For example, schemes based on using SIFT, Viola-Jones, or even HOG. As an example bottom-up approach, consider the following method called semantic segmentation using regions and parts. An image is decomposed into bottom-up regions, or object parts. These individual parts are classified using a set of classifiers into the type of object they are most likely to correspond to, and then results across all these individual parts are fused together into a single semantic segmentation. By comparison, consider feed-forward semantic segmentation with zoom-out features. It uses superpixels mapped to regions at different scales in the image, which it fuses into a larger descriptor before classifying using a fully connected, shallow neural network. You can see the different rectangular boxes in the image corresponding to different parts of the feature descriptor. The regions are named in order from near to far as local, proximal, distant, and scene. Each of these regions allows the feature descriptor to capture spatial and context information at different levels. Hi, in this lesson we looked at how superpixels were super useful for initial attempts at semantic segmentation. But can we do better? can we yet again rephrase the problem we are presenting to the learning algorithm and then essentially get out of its way? That is, letting it learn an optimal solution end to end. Let's find out.